So hi everyone, in this video we are going to discuss about searching. So the problem of locating an element in an ordered list occurs in many contexts. For instance, a problem or program that checks the spelling of words searches for them in a dictionary, for which is just an ordered list of words. So this kind of problems are called searching problems. So what about you? How would you define search? So could it be a search na pageant, or is it in search of a treasure, or could it be a search of true love, or could it be a Google search? So anyway, kidding aside, when we see a searching problem, we have this definition. So given a collection of items, we find an item with specified properties. Okay. And the first searching that we are going to discuss is the linear search or the sequential searching. Okay, and this is actually the simplest of all the searching algorithm, and it uses a brute force approach to locate a target element in a collection. So what is the idea of sequential searching? So we start with the first element in the list or a collection and examine each subsequent element. Okay, so we are going to iterate through each of the elements, and we will stop once we have found the element that we are looking for. Okay, or each element of the collection has already been examined. So here's an example. So we have a list or a collection, and what we want to do is to find a specific element in a list. And the thing is, the list does not have to be sorted. Okay, so here is the pseudocode for the linear search. So the linear search has these inputs, the x or the integer that we are looking for or searching for, and we also have a list or a collection of integers a sub 1, a sub 2 until a sub n. So as mentioned, we will start with the first element. Okay, so we are going to iterate through all the numbers, and we set the location or iterator I as the index of the first element a sub 1. So I is equal to 1. So, and then we are going to loop through our elements using while. And while we have not reached the last element, or while I is not equal to n, and while we have not found the x yet, or x is not equal to, or the number that we are looking for is not yet equal to a certain or specific element in the list a sub I, then we will continue iterating. Okay, it means that the looping will already stop once we have reached the end of the list, or if we have found the element already. So if I is less than or equal to n, then the location is I. So for example, it is in location a sub 8 and the n is 10. So then the location of the largest or the location of a certain integer x is in I. Else, if it is not on the list, that means that we have already iterated through all these items and we have not found the number, then the location is 0, or meaning it is not in the list. Okay, so in order for us to understand this, let us have an example. So we have, again, this procedure, and suppose we have an input, x, or the number that we are looking for is 3. And we have another input or a list of integers a sub 1 to a sub n containing these numbers. Okay, so the a sub 1 would be 4, a sub 2 would be 1, a sub 3 would be 7, and so on. That means that the n here would be equal to 10. Now, the first thing is we are going to assume or iterate through the loop, right? So we will start from the first element. Okay, so the I is equal to 1. Now, we are going to loop through this list and look for that number 3. Okay, next. Since 4 is not equal to 3 and 1 is still less than 10, then we are going to move the index or add the 1 to in the index. Now, I is equal to 2 and the value in the position or location 2 is 1. And 1 is not equal to 3, and 1 or the index 2 is still less than index 10 equals index n equals 10. Okay, so we are going to move our index again, and at this position 3, the I equals 3 or position I equals 3 is still less than n equals 10, and or we have not reached the end of the list yet, and the number in this location is not equal to 3. So we are going to move again. Now, the I is equal to 4, or we are now in position 4, and the number in this location is still not equal to 3. So we move on, and we will continue doing so until such time where we reach a sub 8, or I equals 8, wherein at this part, we find that the number in this location is equal to the number that we are looking for. Okay, and so then the loop will terminate. And since I is less than or equal to n, or meaning the index 8 is still less than n equals 10, or the total number of the integers, then the location is equal to I. So in this case, the location would be 8. Okay, so that means that the location of the number that we are looking for is 8. Now let us have another example. So in this case, what we want to find is the number 11 in the list. Okay, so we have the same set of number 4, 1, 7, 0, 5, etc. Okay, and then we are going to set this as a sub 1 equals 4, a sub 2 equals 1. So now, given the linear search, we are going to start with the first element in the list. Okay, I equals 1. Now, let us start with the loop. The I, which is equal to 1, or the location 1, is still less than the n equals 10, or we have not reached the end of the list yet. And 4 is also not equal to 11. So we are going to loop through, transfer. And now, the number at location 2 is still not equal to 11. So we move on. And we will continue iterating through the list. Okay, until such time where we reach the 10th element, or the last element in the list. So in this case, the loop will be terminated, because in this case, the loop will be terminated because at this point, the I is now 11, and 11 is not less than n, which is equal to 10, or that means we have already reached the end of the list. Okay, and we have not found the number, so else the location would be 0. Okay. Okay, so what would be the running time of the linear search? Or in other words, how long does it take? So if we have a list that has n elements, the worst case scenario is that it takes n steps, or you are going to iterate through all the elements in the list containing n numbers. Okay, so here a step is considered as a single step through the list. So can we still improve the algorithm? Yes, we can. So we can move to front on success, or this is suitable if there's an increased likelihood that item being searched for will be searched again. So meaning, let's say we are looking for a number 3, And you notice that it's usually looked for, or we are going to look for the number 3 often. So what we can do is move the number 3 in front. So we don't, basically cut down the time of iterating in the loop. Okay. So also there's a desire to avoid the cost of moving lots of element, or moving to end on success. So this is used if element is unlikely to be searched for multiple times. So for example, we have a number 0, and we notice that the number 0 is not usually or often looked for or searched for. So we can move the 0 in the list. 0 at the end of the list. Okay, so moving the element to the end when found will improve the performance of future searches. So in the next video, we are going to discuss about binary search.